Hello and welcome to the AICE Chemistry Lecture Series. In this video, we're going to look at Chapter 16, Section 4, which is the last section of Chapter 16. This section deals with elimination reactions, which are the last type of reaction we're going to see for halogenoalkanes, and essentially what is the opposite of the addition reaction that we learn in Chapter 15. Now, with this reaction, we do not need to worry about mechanisms. We only need to learn the reaction itself and what the reactants, products, and conditions are for this reaction. So this is going to be a very short section. Let's get started. Elimination reactions are reactions of halogenoalkanes, which, like I said, are a bit of the opposite of the addition reaction. During an elimination reaction, the halogenoalkane will undergo a reaction where the halogen is eliminated and an alkene is formed. So the alkene will be the final product as far as the conversion of functional groups. So the elimination reaction converts a halogenoalkane into an alkene. So the opposite of the addition reaction where we use the hydrogen halide. So during this reaction, what happens is that the halogenoalkane is going to react with ethanolic sodium hydroxide. Now this is sodium hydroxide in ethanol, very similar to the ethanol solvent we use for the substitution reactions in the last section. Now, the reason why is the same. The ethanol solvent here, the ethanolic part of this reaction, has to happen. We can use aqueous solutions because water can react with halogenoalkanes. So it avoids reactions with water. So anytime we have something that's ethanolic instead of aqueous, it's usually for this reason, that the water is going to react with our organic compound. So in this case, halogenoalkane reacts with sodium hydroxide in ethanol, not aqueous, and the reaction does need to be heated for this to work. So we have heat as our condition here. I'll put here heated. That's our condition. That's why it's double underlined. Halogenoalkanes and sodium hydroxide, ethanolic sodium hydroxide, are our reactants that are underlined. And then our products are going to be two. One of our products in bold is going to be the alkene that the halogenoalkane turns into. And then the other product is going to be a hydrogen halide compound. And again, this is because this is essentially the opposite of the addition reaction of a hydrogen halide to an alkene. So we're essentially just going backwards. Now, a lot of the time you will see this hydrogen halide split up into water. Oops, let me make this a little smaller. Into water and, boy, did that not work. And a sodium halide if we're using sodium hydroxide. So this happens because the ethanol, meaning that there is no water, prevents an aqueous condition where this hydrogen halide could be formed. So a lot of time, instead of writing this as a hydrogen halide, we'll divide up the hydrogen halide into water and a sodium halide. So, for example, if we had something like this, which is 1-bromopropane. One bromopropane would react with the ethanolic sodium hydroxide and heat to essentially eliminate that halide from it, or that bromine in this particular case, and to eliminate a hydrogen that is in the other carbon next door. So that will create an alkene because when these two are broken, a double bond is created between that atom and the atom next door. So we do have to be careful with this reaction though, because sometimes it can lead to multiple products. Like we mentioned before, certain reactions in organic chemistry can have multiple solutions. In this particular case where the bromine is at the end of the reactant of the halogen, it's a terminal bromine, the only double bond that can be formed is with a carbon that's right next door. But what if we had a more complex compound? So let's look at that for a second. Imagine we had a reaction between ethanolic sodium hydroxide and NaOH in ethanol, so we'll just put F, plus this compound. This being 2-bromo-butane. Nothing too crazy. When this reaction happens with heat, what's going to happen is that the bromine in the compound is going to be removed or eliminated. That's what we call an elimination reaction. However, the double bond that can form with both of these carbons. So the double bond could form to the right of the bromine with this carbon, or it could form to the left of the bromine with this carbon. That will lead to two different products. In the case of the left carbon of the pink path, we will get this alkene. In the case of the blue path, we will get this alkene. So if the bromine is eliminated and it connects to the right carbon, we will get a 2-propane. Or sorry, butane, not propane. So we get a 2-butane. Whereas with the other carbon, we'll get a 1-butane. And both products are actually made. When this reaction happens, we get a mixture of both of these products, the 2-butane and the 1-butane, because of how the elimination reaction happens. How the double bond can happen with both the left carbon, with the primary carbon we have here, or with the secondary carbon we have here. So keep that in mind when you're doing these questions about elimination reactions, that those reactions can cause multiple products. Now, that's elimination. It's very straightforward, very simple. That's all there really is to it. The only complicated aspect of this reaction, apart from memorizing everything, is the idea that we can have multiple products. So that's really all the reactions of the halogenoalkanes. It's not a very long chapter. These are all the reactions that we learn throughout this chapter. We learned that alkenes can become halogenoalkanes by the reaction, the addition reaction of the alkene with either a hydrogen halide or a halogen diatomic molecule. Then we learned that in chapter 15. We also learned that that reaction can be reversed and the halogen can be turned into an alkene by an elimination reaction where sodium hydroxide in ethanol and heat are reacted with halogenoalkane. We also reviewed the fact that alkanes can be turned into halogenoalkanes by the use of UV light with a diatomic halogen like Cl2 or Br2, usually in aqueous solution. And that was from chapter 15 as well. We also saw the substitution reactions of halogenoalkanes, the nucleophilic substitution reactions, where we can use potassium cyanide in ethanol and reflux to turn a halogenoalkane into a nitrile. We can use ammonia in ethanol with heat and pressure to turn a halogenoalkane into a primary amine. And we can use sodium hydroxide under reflux or water under reflux to turn the halogenoalkane into an alcohol. Now, these are all the reactions that we learned in 15 or chapter 17, or sorry, 16. But in chapter 17, we will see how an alcohol can be turned into halogenoalkane, and we alluded to this in the first section by using a plethora of different reactants, by using things like PCl3, PCl5, SOCl2, or a hydrogen halide. And we're going to look at all of those reactions in chapter 17. So for now, these are all the reactions of the halogenoalkanes. I'll see you all in the videos for chapter 17 coming up.